Hey there, Adrian Rosebrock here from PyImageSearch.com, and today you're going to learn how to train your first convolutional neural network using Keras and TensorFlow. So far throughout these series of tutorials, you've learned the basics of neural networks, you've learned some of the underlying theory, and then you've also implemented neural networks both from scratch using just Python and NumPy, as well as implemented some basic feed-forward neural networks with Keras and TensorFlow. But since PyImageSearch is a computer vision blog, of course the end goal was to learn how to apply deep learning to image data. Today, you'll gain your first exposure working with image data and training a convolutional neural network on an image data set. So without further ado, let's kind of check out our project directory structure here. We have two driver scripts, ShallowNet animals and ShallowNet cifr 10. These will instantiate an instance of convolutional neural network, load a particular data set, and then allow us to train a neural network on that data set. The animals data set, which you've seen before, is the data set that we're going to be working with. It's a three-class data set of cats, which this particular directory has examples of cat images in it. And then we have dogs directory, which has dog images. And then pandas directory, which has example images of pandas. Our goal is to train a convolutional neural network that can correctly identify what class a given input image belongs to. Inside the PyImageSearch module, we have a number of submodules, most of which we've implemented before. So you've seen our simple dataset loader. This accepts an input image dataset from disk, particularly an input directory, loops over all files in that input directory, parses out the class label, and loads our input image from disk. You can refer back to the previous tutorials in the series if you haven't seen this particular loader before. Inside our neural network module, we have this conv directory, conv. This is where we're going to store our convolutional neural network implementations. And here you see ShallowNet. This is our first convolutional neural network that we're going to implement. It's really basic, in fact, consisting of only a single convolutional layer. And the goal here is just to gain exposure using the particular Keras and TensorFlow functions used to build convolutional neural networks. In future tutorials in this particular course, you'll learn how to build on them, create deeper networks, and obtain higher accuracy. Finally, we have this pre-processing module. You've seen the simple preprocessor before. It takes an input image and just resizes it to a fixed input size. This image to array preprocessor, though, this one's new, and we'll implement this here today. This particular module, it simply allows you to take an input image loaded via OpenCV and represented as a NumPy array, and then convert it into a format that's compatible with Keras and TensorFlow. It's a super simple class, only takes a few lines of code. So now that you have an understanding of what we're going to be actually building, let's see how we're going to do it. So I'm going to come over here to PyCharm, and let's start with our preprocessing module, the image to array preprocessor. So you know the simple preprocessor. All it does is accept an input image and resize it to a fixed width and height. That's all the simple preprocessor does. Now, when training a convolutional neural network, what we do is chain this simple preprocessor with an image to array preprocessor. And we start off here at the top by importing this image to array function from TensorFlow and Keras. This function is responsible for accepting an input image that's a NumPy array and then correctly ordering the channel dimensions. So Keras and TensorFlow, particularly Keras, it can work with different image data formats. In the Theano, which is now a deprecated deep learning library, and particularly in PyTorch, which is super popular among researchers, we represent images in terms of channels, height, and width as a matrix. And then we call that channels first ordering. But in Keras and TensorFlow, we typically represent images in terms of height, width, and number of channels. That's called channels last ordering. For all intents and purposes, if you're using Keras and TensorFlow, then you're more than likely using channels last ordering. It's the default, and it's also what OpenCV uses. But there are instances where you may want to use channels first ordering, or your underlying engine, if you're not using TensorFlow and you're utilizing the Keras library, you may be using a different backend to Keras that may expect you and require you to use channels first ordering. So this class just takes all the guesswork out of that. And we start off here with the constructor, and we have this data format. And by default, we'll set this data format to none and store that inside the class. We can then call this preprocess function, which accepts an input image, and then calls image to array, passing in the image and both the data format. If the data format is equal to none, Then Keras and TensorFlow will inspect the image data and look at the configurations inside Keras and TensorFlow and then properly set the data format. In most cases, it's going to be channels last ordering. However, if you want to specify a different data format, you do so in the constructor, and then this data format attribute here will take care of doing whether you want channels first, channels last, or whatever kind of custom formatting you want to have done. So that's it for the image to array preprocessor. Really, really simple. Now let's move on to implementing ShallowNet, our first convolutional neural network. We start off with some packages here. You've seen the sequential class before. It just builds a graph, a simple directed graph from input to output of a neural network where the input from one node in the layer feeds into the next and so on until you reach the output. Now this conv class, this implements 2D convolution. You will see this all the time when you apply Keras and TensorFlow for creating convolutional neural networks. This is where you learn your conv filters. This is where you specify the number of filters you want to learn, the size of each of the filters, the stride of the filters. So you'll see this class all the time. We then have an activation function class, flatten for taking the output of your convolution operations or your pooling operations and flattening them down such that you could apply a dense layer, which as you know is your fully connected layers. Then we import the backend from Keras. This allows us to check if we're using channels first or channels last ordering, and depending on that, we'll change the input shape to the neural network to accommodate it. Moving on to the class definition, we have this build method. It accepts the width, the height, and the depth of our input images. So the width and height are self-explanatory. The depth is going to be 1 if it's a grayscale or single channel image, or it's going to be 3 if it's a red, green, and blue channel image. And classes here, this is the total number of classes that we're going to be learning. In the case of the animals dataset, there's 3 classes here, so we're going to set classes to 3. Now, let's build ShallowNet. We create an instance of the sequential class and then specify our input shape, assuming channels last ordering. So recall what I said a couple minutes ago. When we're using channels last ordering, which is the default for Keras and TensorFlow, then we specify the input shape in terms of height, width, and depth. But if on the other hand we're using channels first ordering, then we got to change our input shape to be depth first, hence channels first, followed by the height and the width. Again, 99% of the time, if you're using Keras and TensorFlow, you're going to be using channels last ordering. I included this line of code here because I think it's really important to also kind of separate Keras and TensorFlow when necessary and say there are differences. If you want to change the underlying backend and remove TensorFlow and still use Keras, you can do that. And depending on what backend you're using, it may require a different channel ordering. So if you want to manually inspect that inside of the class definition of building your convolutional neural network, this is exactly how you do that. But again, feel free. In most implementations, you could just delete these lines or comment them out. It's typically not going to have an impact if you're using the standard Keras and TensorFlow package. Now let's build the actual network architecture itself. All we've done so far is initialize a sequential object as well as the input shape and dimensions to our network. Now we're going to define a convolution into a ReLU layer. What we use here is the convolution 2D class. We're going to learn a total of 32 filters, each of which are 3 by 3. So learning 3 by 3 filters, 32 total of them, using padding equals same. So the output of this layer is equal to the input shape here. Recall that if you want to use, like, say, padding equals valid, which I believe is the default for the convolution class, then just by how convolution works, you're going to reduce the spatial dimensions of the input image. That may or may not be your desired effect. It really depends on the model that you're implementing. And if you're using strided convolution, then that changes a little bit as well. But for most implementations from your VGGNet perspective, and we'll be covering VGG pretty soon in this series of tutorials, you're going to see padding equals same. And that just means for when inputting an image or a volume into a particular convolution layer, you're going to apply 0 padding such that the output of that convolution layer, that dimension size, equals the input. That's all there is to it. Since it's the first layer in our network, though, we have to specify the input shape dimensions. And the input shape here is based off of whatever we define the input shape to be, based off of whether it was channels first or channels last ordering. So coming out of this convolution layer, we'll apply a ReLU activation. And then again, this is a super simple neural network, hence why I called it ShallowNet. It's just a single convolution and a ReLU. We then flatten that 2D volume, that multi-dimensional volume, and then apply a dense layer with the total number of nodes equal to our classes. You've seen this before earlier in our tutorials on neural networks. And then finally, we'll apply our softmax classifier. This constructed model is then returned to whatever the calling function is. So super simple, very shallow, very compact and small. I mean, this network has less parameters than ones we've trained previously in this series of tutorials. The difference here is that we're starting to get our feet wet working with image data. So I purposely kept this network small and compact. We'll train far, far deeper neural networks later in this series of tutorials. So at this point, we can move on to actually instantiating ShallowNet and training a model on it. So I'm going to open up ShallowNet animals. And let's start investigating our imports. This label encoder here is responsible for one-hot encoding. We'll apply one-hot encoding to our class labels such that we can use categorical cross-entropy as our loss function. We use our train test split function to construct our training and testing split. And then we have this classification report function, which is responsible for taking the predictions from our trained model and comparing them to the ground truth, and then summarizing all that information in a nicely consolidated classification report. Here is our image2 array preprocessor that we just implemented. We have our simple dataset preprocessor, our simple dataset loader, which will loop over all images in our animals directory and then apply both the simple preprocessor for resizing and then the image2 array preprocessor for converting the input image into whatever the proper channel ordering is for Keras and TensorFlow. We then have our ShallowNet architecture model definition. This class is responsible for instantiating ShallowNet, and then we'll train ShallowNet on our animals dataset. We have the stochastic gradient descent optimizer for training the model itself. The paths function from IMUtils. This function is going to investigate the input animals directory, find all file paths in them, and then return the file paths such that we can pass them into a simple dataset loader and load each of these input images from disk. We have matplotlib for plotting, numpy for numerical array processing, and argparse for our command line arguments. And again, speaking of command line arguments, we only need one here, dataset. It's the path to our input dataset residing on disk. So with our command line arguments parsed, we'll find all images inside this input dataset directory, which we do right here. So at this point, we have all images, the paths to all images in this directory. I want to emphasize that it's image paths. It's a string representing the path to where each of these individual files are. It is not the actual image loaded from disk. We're going to do that in just a few lines of code. We then have our preprocessors here. We create an instance of simple preprocessor. It's going to resize each of our input images to 32 by 32 pixels. And each of those resized images are going to be passed through our image2 array preprocessor, allowing Keras and TensorFlow to do any channel ordering modifications. Now, the nice thing about our simple dataset loader is that we can chain these preprocessors together. So when we create an instance of our simple dataset loader, you pass in a list of your preprocessors. This first one, simple preprocessor, again, resizes our image to 32 by 32 pixels. The output of the simple preprocessor is passed into our image array preprocessor, which handles the channel ordering. Calling load here, passing in our image paths, results in the image data, the images loaded from disk, as well as their parsed class labels. We then scale the pixel intensities of the input images from the range 0 to 255 to 0 to 1. So at this point, we have all of our data loaded from disk. So now we need to create a training and testing split. We'll use 75% of our data for training and then 25% for testing. The next step then is to perform one-hot encoding on our training labels and our testing labels, which is exactly what we do here. And then we compile our model. We'll use the stochastic gradient descent optimizer with a small learning rate, and we instantiate our ShallowNet model. The parameters here indicate that the width of each image will be 32 pixels, the height will be 32 pixels, and we're working with 3 channel images, so RBG images. There's also a total of 3 class labels, one for the cats, dogs, and panda class, respectively. We compile our model with categorical cross-entropy loss, since when you perform image classification, if you have more than two classes, and again, more than two classes, use categorical cross-entropy. If you only have two classes, then you use binary cross-entropy. A call to model.fit trains our model. We pass in our training data, train images, train labels, as well as our validation data, particularly the validation images and the validation labels. We use a batch size of 32, and we'll train for a total of 100 epochs. Once training is complete, we'll make predictions on our testing set, and then we'll show a classification report that compares our predictions to the ground truth class labels. And finally, we will plot both our loss, our validation loss, our training accuracy, and our validation accuracy. So let's give this training script a try. I'm going to copy and paste the usage over into my terminal, and I'm going to run the script. So what we'll see here from the output is we start off by loading our input images from disk. There's 3,000 total images, 1,000 images per each class, and then we start the training process. And as you can see, we're training this model really, really quickly, and that's due to the simplicity of the model. It's extremely shallow. There's only one convolutional layer in the entire network, and there's only one fully connected layer, and that's actually what feeds into the softmax to give us our output class label probabilities. So it's incredibly trivial to train this model on such a small data set. Now, as we can see, we're getting about 72% classification accuracy here. And then here you can see our plot. You can see that training loss is falling, demonstrating that our model is certainly learning something. But our validation loss, on the other hand, it certainly is falling, but there's a lot of spikes. There's a lot of volatility going on here. And then we have our training accuracy. Our training accuracy continues to improve, getting all the way to about 86, 87% accuracy. But our validation accuracy, on the other hand, is sitting around 72%. So not as great. And looking at this plot, you can just see how training loss falls at such a rapid rate. And then our validation loss, on the other hand, it falls, but then it stagnates and there's a lot of volatility. It's very, very indicative of overfitting. And overfitting is going to be one of your worst nightmares when training neural networks and performing deep learning as a deep learning practitioner. You're going to be fighting overfitting constantly. And overfitting, what happens there is your model is essentially getting close to memorizing the training set. It's not doing a really good job of generalizing to images. So what we're going to do in future tutorials is study how to improve the ability of your model to generalize to reduce the impact of overfitting. And we'll use techniques like data augmentation and dropout and weight decay and all other types of regularization parameters. For the time being, don't really worry about the actual output results here. Just kind of internalize what the code is doing, really study how we're instantiating these methods here to load our input images from disk, and then also focus on how we're instantiating the optimizer, creating the model, and then compiling it. That's really the key takeaways from this script. Let's look at another example. This one from Cifra 10. The Cifra 10 dataset is built into Keras and TensorFlow, so it's really, really nice to work with just to play around, get some initial experience. So as you can see, I've opened up this script, and let's kind of take a look. Let's see what's going on. We import our label binarization function, going to perform one hot encoding, classification report function to give us a nicely formatted classification report to our terminal. We have the ShallowNet implementation, SGD to train the model. We have our Cifra 10 function. This is going to load the Cifra 10 dataset using Keras and TensorFlow, matplotlib for plotting, and then NumPy for numerical array preprocessing. So calling Cifra10.loadData results in the Cifra 10 dataset returned to us. And notice it's been pre-split, so we don't have to do a training and testing split. We already have our training data here, and then our testing data right over there. From now that it's loaded from disk, let's scale the pixel intensities down from 0 to 255 to 0 to 1, and we'll do that for both our training images and our testing images. We also do some processing on our class labels. So we'll one-hot encode our training labels as well as our testing labels. Here we initialize the names of the class labels inside the Cifra 10 dataset. As you can probably tell based off the dataset name, it's called Cifra 10. There's 10 class labels in the dataset. Shocking, I know. We then have our class names: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So very diverse set of images across the class labels. And as you'll see, these images are really small. They're 32 by 32 pixels. They're like smaller than thumbnails. Like humans actually struggle at times to recognize what some of these classes are because the images are just so freaking tiny. But let's see what ShallowNet can do. Let's see how accurate we can get. We initialize our optimizer and then build the ShallowNet model. Again, each image in Cipher 10 is 32 by 32 pixels. They're RGB images, hence having 3 channels, and there's 10 total class labels. We then compile the model, and then we train it, passing in our training data and our validation data, and we'll train it for a total of 40 epochs. From there, we'll make predictions on our testing set and display our classification report to our terminal. And we'll wrap up here by displaying our training history in a nicely formatted plot. So I'm going to execute this script, put it here in my terminal, and you'll see first that the Cipher 10 dataset is loaded from disk, and we start training. Since there is so much more data inside the Cipher 10 dataset, it's going to take a while to train. So instead of just letting this run for 40 epochs, I'm just going to kill the script and show you my output here. And you'll see that we're getting about 58% accuracy on our validation set and about 76% accuracy on our training set. And I'll show you the plot of our output here. And here you can really start to appreciate the effects of overfitting. Notice how our training loss just has this nice, beautiful descending curve demonstrating that loss is being driven down. We're descending into lower areas of the loss landscape. That's nice. What's not so nice is that our validation loss effectively flatlines after epoch 5. Yeah, there's some minor variation, but for the most part, if you average this out, you just get this nice stagnated line here. That's not good. That means that as we train more and more, we're getting larger and a larger departure from our training loss and our validation loss. They're not decreasing at the same rate, which is typically what you want to see. The same thing is kind of emulated over here in our training and validation accuracy. This purple line demonstrates that our training accuracy is continuing all the way almost to about 80% accuracy, but our validation on the accuracy, it improves a bit, but we're really stagnated near this 60% mark. We just can't seem to get above it. So again, this is overfitting in action. And our goal here is to, in the future at least, is to reduce this impact. We want to see these two curves descending at approximately the same rate. And you want to see these two curves really increasing at the same rate. It's all about overfitting. It's all about applying different regularization techniques and creating your models in such a way and training them in such a way that we reduce the impact of overfitting. But again, I'm getting ahead of myself. I just want to kind of show you some of the impacts of what overfitting looks like. And we have an entire tutorial dedicated to underfitting and overfitting. But I just want to point it out since we're still in the introductory phases, since we're still getting our feet wet. But for the time being, really just focus on this code, internalize what this code is doing, practice running it on your own as well. Download the code to this tutorial or use our pre-configured Jupyter notebooks, run the examples, replicate my results, and then from there, start playing with your parameters. What happens if you change your learning rate? If you increase it by an order of magnitude to make it 0.1, or decrease it by an order of magnitude to make it 0.001. Then train your model. What is the result? How does your learning rate impact overfitting? Also play with your batch size as well and your number of epochs. Recall that if you increase your batch size, there's going to be less weight updates per epoch, and if you decrease it, there's going to be more weight updates. How does that change the result? And if you just want to really test something out, make your batch size equal to the total number of examples in the training set. So there's one weight update per epoch. How does that change the model accuracy? How do you have to increase or decrease your number of epochs to account for that? This is all about exposure right now. Don't worry about getting the highest accuracy possible. We'll get there. We'll absolutely get there. But just play around with these parameters. They're really, really important. I want you to gain some exposure working. So I'll leave you to that now. That's your homework, and I'll see you in the next tutorial in this series.